Alright, let's dive straight into the heart of the matter. We're talking about reinforcement learning, or RL, for those tricky reasoning tasks that LLMs are supposed to be good at. But here's the rub. Traditional RL needs labels, right? Someone has to tell the model what's right and wrong. Now, imagine trying to teach a model to solve complex problems it's never seen before, and you don't have the answers readily available. That's the challenge we're tackling today. We're exploring how to make RL work effectively when you're stuck with unlabeled data, especially during inference. Think of it as letting the model learn and improve itself, even without a teacher holding the answers. So, how does TTRL actually pull this off? The core idea is beautifully simple. Let's train the model using RL, but without needing external labels. Instead, we ask the model to generate multiple possible answers to a question. Think of it as brainstorming. Then, we use a clever trick, majority voting, to figure out the most common answer among these suggestions. This majority vote becomes our proxy for the right answer, our consensus signal. Now, the model gets a reward based on how close its individual suggestions are to this consensus. It's like getting points for being consistent with the group's best guess. Finally, the model learns by adjusting its internal parameters to maximize the chances of getting these rewards. It's a self-reinforcing loop, allowing the model to learn and adapt on its own, guided by the wisdom of its own collective output. Let's get a bit more specific about how the reward is calculated. The reward function is elegantly simple. It's a binary reward. You get a score of 1 if your prediction matches the majority voted label, and 0 if it doesn't. That's it. So, you run the model, get a bunch of answers, find the one that appears most often, and then check each answer against that majority. If it's a match, boom, reward. If not, no reward. It's like playing a game where the goal is to be consistent with the popular choice. The provided pseudocode shows exactly how this works. Extract the answers, count the frequency, pick the winner, and assign the reward based on the match. Simple, yet powerful. Now, let's see if this TTRL thing actually works in practice. We put it through its paces with several experiments. We use different models, Qwen, Llama, and their math-focused versions, to see if it scales across different architectures. We tested them on tough mathematical reasoning benchmarks like AIME, AMC, and MATH 500. We compared TTRL against the original models, their instruction-tuned versions, and even those fancy R10 models that are trained on massive datasets. We used the GRPO algorithm, which is known for boosting reasoning, and carefully tuned the hyperparameters like learning rate and batch size. We looked at standard metrics like pass at 1 and AVG at 64 to measure performance. Basically, we threw everything at it to see what happens. And the results? They're pretty darn impressive. Look at Table 1. Across the board, control gives a significant boost. Take the Q.2.5 Math 7b model on the AIME 2024 benchmark. That's a 159.3% improvement. That's not just a tweak, that's a massive leap forward. Even when applied to the smaller Qwen 1.5b model, it still saw a huge 142.4% jump on Math 500. On average, across the three tasks, the improvement was a solid 84.1%. What's really striking is that these gains are achieved using only unlabeled test data, and yet, it often beats models trained on massive labeled datasets. This suggests that Tuntrel is tapping into a powerful source of learning potential that's been overlooked. It's not just about getting better, it's about scaling and generalizing. We found that Tuntrel naturally scales. Bigger models, like Qwen 7b, tend to benefit more from Tuntrel than smaller ones like Qwen 1.5b, especially on harder tasks like AIME. This makes sense. Larger models have more knowledge to leverage during self-improvement. And it's not just about the specific task it was trained on. We tested the models on other benchmarks, like AMC and Math 500, and found that Tuntrel's improvements generalize well. It's not just memorizing the training data, it's learning more general reasoning skills. Plus, we tried using different RL algorithms, like PPO, and got similar results, showing control is flexible. So, how does control actually learn during training? We can't directly see the ground truth labels, but we can track some useful metrics. We monitor the entropy of the model's outputs, how uncertain it is. We look at the majority voting reward, the majority ratio, the accuracy of the estimated label, and the accuracy of the reward itself. Figure 5 shows these curves for training on AIME 2024. You can see the accuracy generally goes up, while the entropy tends to decrease. These metrics help us understand the learning process, spot if things are going off track, and decide when to stop training, picking the best checkpoint. Okay, let's get philosophical. How well can TTRL actually perform? The first big takeaway is that TTRL is surprisingly good. It doesn't just match the baseline performance of the original model, the MAJ at N score, it actually surpasses it. It's like the student learning from the teacher, and then surpassing the teacher's knowledge. Even more impressively, the performance of TTRL trained on unlabeled data gets very close to what you'd get if you could directly train the model on the test data using the ground truth answers. That's a huge leap, suggesting TTRL is a very efficient way to learn, even without explicit labels. Now, why does this work? It seems counterintuitive, right? You're learning from potentially noisy labels. But here's the magic. RL is surprisingly robust. First, it turns out RL algorithms can handle some level of reward noise. They're more interested in the direction of the reward signal than its absolute accuracy. Second, the way rewards are calculated in TTRL is crucial. Even if the majority vote isn't the true answer, if the model predicts something different, it still gets a negative reward. This helps guide it away from bad answers. Also, interestingly, the rewards are often more reliable than the labels themselves. Figure 8 shows the label accuracy is low, but the reward accuracy is much higher. It's almost paradoxical. Sometimes, a less capable model might actually produce better rewards for itself because it's making more diverse mistakes, which helps distinguish correct answers from incorrect ones. Of course, no method is perfect. When might TTRL stumble? Two main things. First, if the model doesn't have enough prior knowledge to handle the task in the first place, it's going to struggle. It's like trying to teach a toddler calculus, they need a foundation first. Our experiments showed that on very difficult problems, the improvement from TTRL drops off. Second, the hyperparameters matter. You need to tune things like the temperature and the number of episodes carefully. Get it wrong, and the training might fail, as shown in Figure 10. Finding the right settings is key. So, control isn't a magic bullet, but it's a powerful tool when used correctly. Where does this fit in the broader picture of LLM research? Control builds on the idea of test time scaling, which is all about boosting model performance when you're actually using the model. Think of it as turbocharging the inference process. Within TTRLs, there's test time inference, which is about generating better answers, and test time training, which is about adapting the model on the fly. TTRL is firmly in the test time training camp, but with a twist. It uses self-generated labels. It also connects to the huge field of RL for reasoning, like RLHF, which uses human feedback to align models, and GRPO, which uses rule-based rewards to improve math solving. TTRL is the next step, exploring RL where the model learns from its own experiences without needing external labels. So, wrapping it up, we've introduced TTRL, a new way to train LLMs using reinforcement learning directly on the test data they encounter, even without labels. The key innovation is using majority voting to create a reward signal. Our experiments show it's a powerful technique, leading to significant performance gains across different models and tasks, and even approaching the performance of models trained on labeled data. We see TTRL as a crucial step towards models that can learn continuously, adapt to new environments, and improve themselves over time, fueled by the experiences they generate. Now, let's be real, this is just the beginning. We're still exploring the full potential of TTRL. We need to dig deeper into how prior knowledge and hyperparameters really affect the learning process. Looking ahead, there's a lot to do. We need to understand the theory behind it better, prove it works mathematically, We want to see how it performs in real-time scenarios, adapting to streaming data. The ultimate goal is to scale this up, applying it to massive datasets and models, and even use it for complex tasks like scientific discovery or building intelligent agents. It's a long road, but the potential is enormous. Just to clarify some terms we've been throwing around, test time scaling is the umbrella term for boosting performance at inference time. Under that, we have test time inference, which focuses on generating better outputs, often using techniques like majority voting or best of n. And then there's test time training, which is about adapting the model's parameters during inference, which is where TTRL fits in. It's all about making the most of the computational resources available when you're using the model. Finally, if you want to try this yourself, we've provided a detailed list of hyperparameters in Table 4. This is the recipe we used to get the results we saw, specifically for the Quen 2.2.5 Math 7b model on the AIM benchmark. Things like learning rate, batch sizes, temperature, the number of episodes, and various optimization tricks. It's all there, so you can reproduce our work or experiment with your own settings.